thought that probably the best approach was to give a seminar, given the interdisciplinary audience we have here with many biologists as well as astrophysicists. I have preferred to give a seminar quite basic, from a point of view, very basic, and also filled with pretty images. So I hope if you get bored, at least you have the images to delight yourselves. Okay, so I'm going to talk about planetary nebulae. What are planetary nebulae? These are some examples of this kind of objects in the sky. They are everywhere. They are nebulous. They are faint, quite faint. They are symmetric, as you can see, to different degrees. Most of them have a star in the center. You can see in like here or there, star in the center. And on top of all of that, they are very different from one another, as you can see. So what are these beasts? What's the origin of this name, of this planetary nebula name? And what's the origin of their shapes, of their very different shapes? Are they important in the grand scheme of things in the universe? Well, we'll try to partially answer these questions, but let's start at the very beginning. This is the first planetary nebula ever discovered. It was discovered in 1764 by Charles Messier on the night of July the 12th in the Vulpecula constellation. It's now called M27 after Messier's catalog, is his 27th object. Messier noted the presence of several of these nebulous objects in the night sky. He mistook them for comets at the beginning, at first. But then he compiled a list of them so others wouldn't make the same mistake he did. This is an image, an illustration rather, by Father Angelo Secchi, like 100 years after the discovery of Messier, and we see this nebula. This is the image of this nebula that we are most used to nowadays, as seen by the very large telescope at ESO. This nebula, after its discovery, attracted the attention 18 years after its discovery, attracted the attention of two musician siblings turned to astronomy, who would revolutionize astronomy. Thus, on September the 30th, William Herschel, one of these siblings, wrote, "My sister discovered this nebula this evening in sweeping for comets. On comparing its place with Messier's nebulae, we find it is his 27th. It is very curious with a compound piece. The shape of it, though oval, as Messier calls it, is rather divided in two, as opposed to the description given by Messier, which is that one." So this is a first indication that of the complexity of the shapes of this nebula, that even two different astronomers have different opinions on the morphology of this object. Well, it was an incipient mystery. Here's another discovered in 1779 by Antoine Daquet de Pellepoix, M57, which is, a very dim nebula, he said, but perfectly outlined, as large as Jupiter, and resembles a fading planet. We are starting to see this planetary nebulae term, where it comes from. This resembled a planet in the solar system. This is a more modern view of the same nebula, which is the Ring Nebula, NGC 6720, also called. Herschel, William Herschel studied this subject very extensively. In a letter to another astronomer, a French astronomer called Jérôme Lalande, he wrote, these are celestial bodies of which as yet we have no clear idea, and which are perhaps of a type quite different from those that we are familiar with in the heavens. These bodies appear to have a disk that is rather like a planet, that is to say, of equal brightness all over, round or somewhat oval, and about as well defined in outline as the disk of the planets. So he was clearly very puzzled by these objects, and he had reasons to be. Indeed, 18 months earlier, he had found a nebulous star, or perhaps a comet, in his own words, which drifted very slowly among stars, among the firmament, meaning that it was a solar system object. In fact, it was a planet. He at first thought it was a comet, but it was a planet, which was called Planet George, after George III, the King of England. For maybe like 40 years or so, now we know this planet as Uranus. So the first thing Herschel did after discovering this nebula, this very curious nebula, was to check if it moved among the stars. 90 minutes later, he checked, it hadn't moved, obviously, but he continued to check several weeks later, and even 16 years later, he was still trying to prove whether this object was a solar system object, or on the contrary, it was very far away. He died without knowing. In fact, we have to realize, this is a modern view of this nebula that we call the Saturn Nebula. That's the nickname. That's a good nickname considering the shape, at least to primitive telescopes. We have to consider that back in this time, we had no idea about almost anything, okay, up in the sky. In fact, we didn't know how far other stars were. Have no idea. So Herschel and his sister, Caroline, together observed the sky for decades and cataloged a lot of these objects. They cataloged around 2,500 nebulae and clusters of stars. In this huge list, there were 78 planetary nebulae in this catalog. Now, the first problem was that they were very different from one another, as we have seen. So they classified them as class 4 objects, which was a category, a ragbag for listing every anomalous object. Planetary nebulae, stars with bursts, with milky chevelure, with short rays, remarkable shapes. So everything that they didn't know, they put in this class 4. Nowadays, we know that most of the objects in this catalog are what we now know as galaxies. They didn't even know that the Milky Way was a galaxy, so imagine, okay? But back in this time, the galaxies were as mysterious as planetary nebula. And this, by the way, this planetary nebula, the term is often attributed to Herschel because of the catalog. It's not clear that it's his deed, okay? But look at the inertia that some names have, that we still call them planetary nebulae when we know that they have absolutely nothing to do with planets whatsoever, okay? But still we call them that way, and there's no way that we can change the name. There's too much inertia, okay? Now, one of the first things that they wondered about these objects was, are they clouds of gas or stars so far away, that so crowded by distance, that we see them as a fuzzy cloud. The first one to give an answer to this was William Huggins, an English astronomer and a pioneer in spectroscopy, who proposed to use spectroscopy to determine the nature of this nebula. He said, prismatic analysis, if it could be successfully applied to objects so faint, seemed to be a method of observation especially suitable for determining whether any essential physical distinction separates the nebula from the stars. Okay, here we have a planetary nebula and a galaxy. Now we clearly distinguish them both. Okay, to the telescopes back in that day, they were quite similar, and maybe they could mistake this appearance for this one. In here, we see that we know that there's a lot of stars. Basically, those are all stars. There is gas as well, but we see it fuzzy because the stars are very far away in galaxies, and they are crowded by the distance that between the galaxy and us. But in this case, there's something else, something different. So William Huggins applied spectroscopy to study these objects. As you know, spectroscopy, spectral lines are chemical fingerprints of the components in the object we are studying. Here we have these beautiful illustrations by Father Angelo Secchi of the 19th century of the spectra of different kind of objects in the sky, mainly stars. And as you can see, spectra are like black body radiation, so it's a continuous spectrum with absorption with holes, like absorption lines, which are indicative of chemical elements. The spectra of planetary nebula is quite different. As you can see, this is a spectrum of a planetary nebula. And you can see here that it's an emission spectra, not an absorption spectra like we have seen before. And it only has, there's no continuum, and there's only spectral lines. So Huggins concluded that these objects must be enormous masses of luminous gas. Here we can see this is the spectrum of the ring nebula, of this nebula. This is the wavelength in this direction, and we have the nebula appearing there in each spectral line corresponding to elements that are present in these clouds of gas. Okay, now that we know that, we can wonder about what is the source of this energy output. The nebula are bright, they emit, they must have an energy source. Why do they glow, in other words? Well, Edwin Hubble in the 1920s, look, this is just 100 years ago exactly. So keep in mind that the knowledge of these objects have improved quite rapidly in the last century. Hubble, the same Hubble, you know, after the expansion of the universe, compared the apparent size of a sample of these nebulae to the brightness of the star in their center, and concluded without any doubt that the central star must be responsible for illuminating the nebula. That's the energy source. But more precisely, we can say a few years afterwards, Donald Menzel used atomic physics, which were kind of new, to conclude that the atoms forming the nebula, the cloud, are ionized. They are stripped of electrons by high energy photons coming from the central star. So more precisely, they are ionized by the central star. Even more precisely, we have a few years later, 1927, Hermann Sandstra derived the temperature of these clouds of gas from the flux of the H beta line, one hydrogen line in the optical range, and concluded that the central star must be way much hotter than normal stars like the sun. But what happens to the temperature of stars? Why are some stars hotter and others much cooler? Okay, we are already in the 1920s, and we still don't know even that. We were only beginning to realize that the Milky Way is but just another galaxy among hundreds of billions of galaxies. But this is the same epoch in which we discovered that. In this time also, in the early 20th century, it was believed that stars were born very hot and evolved, they cooled as they evolved. They evolved towards cool temperatures. And the stellar classification back in that time was based on the depth on the intensity of the hydrogen lines in the spectrum of stars, in the spectra of stars. It was Annie Jump Cannon, one of the famous Harvard calculators, who found a much more sensible system of classification, which classified the stars according to their effective temperatures, to the temperature of their surface. This here is a mnemonic, very famous mnemonic, which classifies stars from the O-type stars, O, B, A, F, G, K, and M, which goes from higher temperatures to cooler temperatures. Here you have the spectrum of this different order set of spectral types, and here you can see the typical spectrum of each stellar type. O and O stars, B, A, F, G, K, and you can see here that O stars emit most of their flux in the ultraviolet and the blue side of the wavelength range, and as we go down, the peak of the emission goes towards the red. That means, in a black body radiation, that stars are cooler. So, if we apply this to the planetary nebula, at this time, as I have said, it was thought that the central stars of the planetary nebulae, since they were very hot, they must also be very young. But Herbert Curtis in 1918 showed that the distribution of planetary nebula in the galaxy is coincident with that of all stellar population, which are essentially meaning all stars. And this raised doubts about central stars of planetary nebula being very young stars. It didn't show that they were associated with all stars, that they were linked to all stars, but it was a very rare hint pointing into that direction. But back in this time, we didn't even know what powered stars, okay? The solution to this started to come from Arthur Eddington in the 1920. The source of energy that sustained the stars, as I have said, it was unknown. They have absolutely no idea. Keep in mind that this was little over a century ago. So my grandparents were already alive in this time. Eddington, in a very smart, with a very smart idea, he speculated with the correct solution. He anticipated it in a time when nuclear fusion or fission even had not been discovered. And he concluded that given the difference on mass of 4 hydrogen atoms and 1 helium atom, he speculated with this fusion of hydrogen into helium, and he said if only 5% of the star's mass consists initially of hydrogen that the total heat generated with that energy of the difference in mass of this helium atom and the 4 hydrogen atoms will suffice for our demands of energy that we observe in the sky. So, and he added quite cleverly, if indeed the subatomic energy in the stars is being freely used to maintain their great furnaces, it seems to bring a little nearer to fulfillment our dream of controlling this latent power for the well-being of human race or for its suicide. This cannot be more, I don't know how to say it, but could have been in the present as well. Okay, but still we didn't have a clue of what the stars are made of, okay? The solution to this came by the hand of Cecilia Payne, another of these Harvard calculators who made a huge contribution to astrophysics. Her proposal, made in her doctoral thesis, was that stars were fundamentally made of hydrogen. And therefore, hydrogen, well, that was the explanation to why hydrogen is the most abundant element in the universe. This idea was not taken seriously at this time because it didn't make sense that the Earth and the Sun had essentially different compositions. For the other elements, not hydrogen and helium, she got abundance ratios very similar to those observed in the Earth. But by far, the most abundant element was hydrogen, followed by helium, which are very, very rare on Earth, very scarce. In fact, it was another astronomer, Henry Norris Russell, the one after the Hertzsprung-Russell diagram, who convinced Cecilia Payne to say in her thesis that to attribute this finding to a probable error, some kind of spurious result, probably erroneous. As you can see here, this is from her thesis. The outstanding discrepancies between the astrophysical and terrestrial abundances are displayed for hydrogen and helium, and the enormous abundance derived for these elements in the stellar atmosphere is almost certainly not real. Russell convinced Cecilia Payne to include this as the conclusions of her thesis. Years later, in 1929, Norris Russell realized his error when he checked this for himself. And then he credited Cecilia Payne, but even so, the credit was still given to him for quite a long time. In fact, the Cecilia Payne's thesis was described by another astronomer, by Otto Struve, as undoubtedly the most brilliant PhD thesis ever written in astronomy. So you can see its importance. We can apply this to planetary nebula now, okay? Years after, several decades after this, this was the beginning, this discovery together with atomic physics as a whole was what we needed to start developing evolutionary models of stars, okay? And after this, we could develop some kind of family tree of stars. For stars less massive, with the mass less than 8 solar masses, up to 8 times, stars have a main sequence after which they grow as giant stars, as red giants. The hydrogen is depleted in the core contracts, the envelope expands, and it swallows the inner planets. And well, then there's another giant phase called the asymptotic giant phase, asymptotic giant branch, the AGB phase, and then stars evolve as white dwarfs, which is just the core of the star, the inert core. It's just a corpse without any nuclear reactions, and it's very hot. That's why they the central stars are hot, and it's very, very dense, incredibly dense. Now, Joseph Shklovsky suggested in 1958 that planetary nebulae were in between these two objects. They were the descendants of red giants and the progenitors of white dwarfs. Now, again, we are talking about 60 years ago, a little bit more than 60 years ago. My parents were in school back in this time. When they studied, we had no idea absolutely where to put these objects, planetary nebulae, in the family tree. Okay, this reached textbooks many years later, of course. Okay. Now, so stars, by the way, in this diagram, this is not to scale. Okay, this is much, much larger than this, and this is much, much, much larger than this, and this is much, much, much smaller than all of this. Okay, but more of that later. Now, the idea is that these nebula are actually the envelope of a giant star blown away, slowly blown away, came from George Ogden Abel and Peter Goldreich. They suggested that that the envelope of an AGB star, which we can see like this is the envelope, here's the core, this is blown away very, very smoothly, very slowly, and this becomes the planetary nebulae. Because they suggested this because the expansion velocities we could see thanks to the spectra of the nebula were very similar. The expansion speeds of the pulsation of the envelopes of the AGB was quite similar to the expansion velocities observed in planetary nebulae. Now, let's get an idea of the size of planetary nebulae. This is a family picture of the solar system. The Earth, we have the Earth here. This is the Earth, okay, a reference in size. This is the Sun. The Sun is much larger than the Earth. These are the objects in the planet of the solar system, different planets, the orbits to scale. This is the Sun, and the orbits of the Earth is around there. And we have the orbits of the outer systems like here, okay? Now, if we put the orbits of the whole solar system, we can put it compared to this image of this huge supermassive black hole in the M87 galaxy that you know of, this image. Okay, so this is the Sun here, this is the orbit of Pluto, this is how far the Voyager 1 has reached. Okay, this is the black hole, and let's put this black hole compared to a planetary nebula. Okay, this is, well, the event horizon of the black hole is approximately this size. Now we have a planetary nebula. This is NGC 6302. This also called the bug nebula or the butterfly nebula. And can you see the black hole over there? Okay, the black hole is this size, the supermassive black hole. So imagine how large are these objects. This is a few light years across. Okay, so they are really huge. They reach several light years from end to end. Now, if we know the distance between the planetary nebula and ourselves, and the Earth, which is very complicated to obtain, by the way, but that's another different story. And we know also the speed, the velocities at which they expand, we can rewind that movie, okay, to have an estimate of their ages. How old are they? And we find that they are in the range of from up to several thousand years. For example, this nebula, NGC 7027, is as old as the Colosseum in Rome. This other one that we have seen is as old as the Great Pyramid of Giza. This one, the Necklace Nebula, is as old as the oldest building that we know of, which is in Göbekli Tepe. I think it's in Turkey or around. I'm not sure, or Iraq, probably, rather. Okay, but they are not much older than this. They are about up to maybe 20,000 years after they are expelled from the star. They get too diluted in the interstellar medium so as to see them. Okay. Now, this is a diagram that in astrophysics we call a Hertzsprung-Russell diagram, which is useful for evolutionary purposes. We have the temperature of the stars here. This increases in this direction to the left, and there's the luminosity of the stars here. And stars, as they evolve, they travel around this diagram as they get old and traverse different stages. Our star starts in main sequence. This is a star rather like the sun, with one solar mass star starts in this place, and then as it gets to the red giant branch, it increases in luminosity and gets cooler, and there's another stuff, and then this asymptotic giant branch, and then stars. Here we have, when the asymptotic giant branch finishes, the nebula is ejected, and we have the post-AGB stage where the central object is becoming a white dwarf, and then its luminosity stays the same, but it gets progressively hotter and hotter until it reaches a stage, a temperature in which it emits enough ultraviolet photons to ionize the nebula around it. This is stellar evolution in a nutshell. Okay, this model comes essentially from Paczynski, which in the 70s elaborated a simple model of these AGB stars, which is basically are removing the outer layers of their own envelope and traverse this path. The speed at which they evolve in this path depends a lot on the initial mass of the star, and also the mass of the core of the star. The most massive ones would not be observed because there would be not enough time. It would be too much of a chance to observe a very massive one, because they evolve very quick. And the less massive ones, either because most of them are way too diluted into the interstellar medium before the star has reached enough temperature to ionize the nebula. Now, we not only have ionized atoms around, but also we have planetary nebula are made also of different components, which are neutral atoms, and also molecular. There's a molecular component as well, because it's very cold, and atoms get together and join together and form molecules. This, since the advent of radio astronomy, we have been able to observe this other component of planetary nebulae. We also have seen that there's much more beyond this ionized region that we see here. In some of them, in fact, we have been able to detect through very deep exposures, we have been able to detect a halo that we associate with the emission. This is the halo of this planetary nebula, the Cat's Eye Nebula. Is much larger than the nebula itself. This is very tenuous hydrogen, which in this case it's ionized hydrogen, but very tenuous. And we associate these halos with emission from the wind debris of the AGB. So now we have more or less the whole picture. We have a cycle of life. Okay, We have some butterflies that butterfly-like objects that deposit their pollen to form new stars in a cycle. This is the massive star cycle. We are not much interested in this talk, but we have this in this low mass star cycle. We have the sun, well, star forming nebula where stars are formed, a sun-like star, then red giant, then planetary nebula, then white dwarf, and also the material from the planetary nebula is diluted into interstellar medium. It enriches it chemically, and new stars are born from that. So we already have a qualitative idea about what these planetary nebula are. They are a final stage of the star's life in low and intermediate mass stars, but we still have some questions to answer. First of all, how many of them there are, and also why are they so important so as to give an almost hour-long seminar about them? Well, let's start wondering about how stars die. If we ask this question back in the street, 9 out of 10 people will answer, okay, stars die exploding a supernova. No problem about that, okay? And the other one, the 10th, will just shrug their shoulders and I don't know, have no idea, I don't know, okay. Now the fact is that only 1 in 100,000 stars die as supernova. Most stars in the universe, that is 9 out of 10 stars, die quite unspectacularly, okay, without making a big fuss of it, without making any noise. They die quite unnoticed, okay? But 1 out of 10, which is 10%, is not a bad percentage, okay, have the mass between 0.8 solar masses and approximately 8 solar masses. They reach this AGB stage, this asymptotic giant branch stage, and they die as a planetary nebula. We, in fact, think that this will be the fate of our sun. Now, why are low and intermediate mass stars so important? Well, because there are so many of them, as we have seen, that the chemical enrichment of the interstellar medium coming from them is quite significant. In fact, you are partly made of stuff synthesized in low and in these stars, in low and intermediate mass stars. They contribute significantly to the chemical enrichment of the galaxy, not only by producing carbon and nitrogen. See, this is in yellow we have coming from low mass stars, stars ending their days as planetary nebula. And also, well, there's some about this because they can produce a kind of supernova involving white dwarfs. But let's get with the yellow stuff. Most of the carbon in the universe, most of the nitrogen are produced in these stars, and also a good fraction of heavy elements is produced in these stars through a process which is called the slow capture of neutrons. It's different from the process in supernova for producing heavy elements, which is rapid capture of neutrons. Supernova, they are much less in number, but the importance is more or less 50-50 in heavy elements. But because of low mass stars produce very few quantities of these heavy elements, but there are so many of them that in the end, almost half of it comes from these stars. Now, we have a qualitative idea of what these objects are, what are the final stage of this life of the stars. We have talked about the cycle of life in the universe, how they enrich the medium. They are cosmic butterflies, but how are these butterflies shaped exactly? How do you actually make one? Okay, first models of formation came in the late 70s, early 80s. This is a model by Sam Kwok. There are several formation theories. We need, in a word, we need to eject the envelope, and maybe dynamical instabilities, either pulsational instabilities, shell oscillations due to thermal instability of the core. We have radiation pressure, we have thermal pulses, we need radiation pressure from the light, from the star, to avoid fallback of material back into the star. But do all of these processes, are they at work here or not? Okay, so the first of these models is basically based on winds. The star, basically the giant star produces a wind, which is, this is the AGB wind, very slow, like 10 kilometers per second or so, which in astrophysics is very slow. And this wind is very dense also. And when the stars evolves enough, the wind it produces changes the mode, and it produces a wind which is much faster, of the kind of 2000 kilometers per second, and much more tenuous. And this wind catches the other one because it's much faster, and it shapes the nebula. Okay, so with this model, we can produce nebula like this one, which is round. We know how to produce round planetary nebula now, okay? And yet, most of them are not round at all. Most of them, like 80% or so, have some kind of symmetry organized around an axis, a symmetry axis. They are bipolar in a way. So how to explain this? After all, a star is quite round, no? It's essentially round. How do you make a bipolar nebula out of a round star? Well, there are different theories, but I'm going to focus on this one, common envelope evolution. It was known that novae and binary systems sometimes, if you have two stars orbiting close to one another, when one of these stars evolves and reaches the AGB stage, it grows, and then if the other star is close to it, then on evolving, this star can feel its Rhodes lobe, can grow so much that some of the material of this star travels to the other one. And then you end up with essentially the star, this is the primary star, swallowing the other one, which is now that both stars now share the same envelope. And this star, due to drag forces, spirals inwards, so the orbit of the stars shrinks progressively until you have a very much tighter orbit, and due to some processes, the angular momentum that you have, this is a reservoir of angular momentum, because you have the star orbiting very far away. If you end up with a star, much closer, then you have a lot of angular momentum there to help you eject the nebula. These nebula are ejected here. The nebula is ejected after a very brief. This stage is very brief. It would last only for 1 or 10 years, something like that. And then the envelope would be ejected, and the envelope would be what we observe as a planetary nebula. Have a video of this process of common envelope. We have these two stars here as they evolve. I've marked the initial separation that the stars had at the beginning of the video, and well, there's the duration of the time is not displayed here, but this whole video would take place in, let's say, 1 year or around, or maybe up to 10 years or so. And as the stars spiral inwards, they get closer together and they end up orbiting much faster because the orbit is much tighter. See that the separation here has decreased a lot from the initial value. This would be another representation of the same phenomenon. We are seeing here, we are seeing from the top, and here this is an edge-on view. These two stars are in this plane. And this is the envelope at the end of this process would be suddenly ejected. Now, this was developed by Paczynski as well in the 1970s, and it looked very promising to explain these bipolar shapes. But problem is that no binaries are found or were found. Barely a pair of them, just a bunch of them. So virtually, let's say none. Okay, so this couldn't be the explanation. Maybe we resorted to some other explanations involving magnetic fields or rotation or different stuff. But there were more problems. In 2001, Valentin Bujarabal and collaborators found that in about 80% of preplanetary nebula, which is a stage which comes right before the planetary nebula stage, that is before the nebula gets ionized, and these are nebulae which what we are seeing here is not ionized, basically it's not ionized, well, it's ionized not because of the central star, but because of shocks, and they also have a lot of molecular, most of them are basically formed of molecules. But in 80% of these objects, they have very fast molecular flows, and these flows have the momentum, the linear momenta are just way too high to be powered by radiation pressure. Radiation pressure, pressure from light from the central star, was not enough to explain why these flows were moving so fast. In fact, in some cases, the momentum of the outflow is 1,000 times larger than that carried by radiation pressure. So they said, due to the lack of theoretical studies back in this time, the possible momentum source remains a matter of speculation. A year afterwards, we had this paper, very good paper by Bruce Palik and Adam Frank, with a generalized model of formation of these objects. Now we don't need to worry about making round or bipolar objects because we have them all here. There was a review with different possibilities, investigating different possibilities involving different phenomena, like magnetized wind-blown bubbles, and some of them needed some deposit of material here, like in a ring, very dense and very massive. So the flows from the star would preferentially come through with a symmetry axis, and so on. We have also this common envelope stuff here. It was quite a review. So basically, that's more or less the present, let's say. We've reached the 21st century. That's where I came in when I first started my PhD back in 2002. And well, and just for the final minutes of the seminar, I will give you just a quick summary of I don't know, interesting things that I have been involved in Also, I hope quite pretty. This is an object I studied in my thesis, as you can see here, if it goes, okay. We don't have one, let's say, component, but up to 4 different components, all ejected, in this case, ejected sequentially. So things are a little bit more complicated than we have seen before. Another thing that it's quite nice was a monitor study to this nebula, which is M29, which is actually a lighthouse up there. See this thing, it gets rotating with time. Probably, maybe you can see here. Ah, yes, you can see it there, that you have here the year. In the last couple of decades, it has rotated quite a bit. Thanks to this, we estimated the orbital period of the binary system that should be here, because the orbit is so tight compared to the distance with to the object that we can't clearly see that there are 2 stars in there. Okay, but there must be 2 stars because of this rotation of this lighthouse. Also, another study that I made with the ALMA interferometer in the submillimeter with CO in molecules. This is this nebula that we already know, and we found here a huge ring that this is the first time with this interferometer that this gets so resolved. This is like a high resolution image of this ring that is in the equator of the nebula. It's quite massive, and here we saw that there's not only one ring, but there's another kind of ring which is much younger, and it was ejected later, and it has more or less the mass of a Jupiter planet. Also, remember this binary stuff by Paczynski? Well, we thought at some point, the community thought that there were some morphological features like rings, jets, and low ionization structures that could help us distinguish which systems had 2 stars, 2 very tight stars, these close binaries undergoing common envelope in their cores. We started a campaign in 2009, and we observed a bunch of these objects, and over a 6-year period, we doubled the number of known planetary nebula with close binary nuclei. We published a few papers dealing with this, one of them in Nature, that got me here to give a seminar, by the way, a few years back. And well, basically the thing that we did was to monitor, to take images in certain filters of the central stars of these nebulae, and see that with time, the brightness changed with time in this fashion. This comes basically, in this case, it comes from the 2 stars being distorted because they are too close to one another, and depending on the surface they are presenting at you. Here we have more surface of star, here we have less, so the brightness is less. Here we have other the full surface that we can see, the less, more. And if you study the spectra with via radial velocity, you can get the radial velocity of the star via some spectral lines, and you can solve their orbits. You can solve, you can get the masses of the stars, the separation, and so forth. So if we do that, which is very costly because of the spectra, to take in radial velocities is very costly. You need large telescopes and a lot of time. But in every system, now we know about almost 100 binaries, close binaries, giving rise to planetary nebulae. We think that like 20 or 25% or so of all planetary nebulae, at least 20 or 25% come from these binary stars. And on top of that, we, in all the objects, which are so far, it's like 8 objects or so, in which we have been able to measure the orientation of the nebula, which is easy, and also which we have been able to get the orientation of the orbital system, we see that they are coincident. Which is, by the way, it's required by the model that I have talked about of these closed binaries that get shrink, the orbit shrinks, and then the nebula is ejected. It's ejected preferentially in a bipolar shape in the directions basically perpendicular to the, well, most of the material is actually in the equatorial plane, but they have like this bipolar shape. And the alignment works perfectly when you are able to measure both things, the inclination of the nebula and the inclination of the binary. This means there's a 1 in a million chance that this is just by pure luck, okay? So Paczynski was right, and planetary nebula can be shaped by these closed binaries. Well, just to finish, to wrap things up, this is an image that you know of, the two in the bottom of the NGC 3132 nebula. These are images from the James Webb Telescope. You can see here a different component than that the Hubble image is showing. Here you can see a lot of molecular hydrogen in the outskirts of the nebula, and here you can see clearly these two stars. Well, we have a paper in the community in which a lot of people have contributed, led by Ursula De Marco, which was accepted in Nature Astronomy, and I can't tell you anything about it because it's still embargoed. Well, next week probably it will be published and there will be press releases and so on. So, concluding, over the last 2.5 centuries, we have understood a lot of things about these strange beasts, but there are still a few things that we do not understand. But we know that stars between 0.8 and 8 solar masses die as planetary nebulae, like butterflies among the stars that deposit their pollen, which is basically hydrogen and other chemical elements synthesized by the star, that will serve to form new stars, planets, and perhaps even beings that wonder how the star that illuminates them will die. We know that our sun will end their days in around 6,000 million years from now, 6 billion years. And we know, we think that the nebula it produces when it dies will be round. And if it's not, well, I won't be around for complaints anyway. So, and that's all. Thank you very much.
Thank you very much, Miguel. We will start now with a short question time. Those of you in Zoom can ask questions like either verbally or by writing them in the chat. And those of us here, if anyone has a question, please ask. Okay.
Hi, Miguel. Very nice talk. I enjoyed it very much. I have many questions, so I'm not sure if I can ask all of them. Let me ask you the easy one.
Yes,
so,
yes, please.
No, they're all easy. So from the massive stars community, we've copied this idea of the common envelope phase, so which we basically use to explain everything we cannot explain. So my question is, have you caught any of these stages with observations? Could you tell us something like that? Because sometimes we are seeing a spectra that is like, oh, maybe they are in common envelope, but I really don't know what I'm looking for to say the stars are really in a common envelope. So
Yeah, it's very difficult because this stage is supposed to last just for maybe 1 year or so. So observing one would be very difficult, even though there are lots of stars traversing those stages. But there are some indications that some objects, for example, I think that water fountains, objects called water fountains because they are they show water masers, and they are approximately in these late stages of stellar evolution. They could be objects coming out of this common envelope stage. They could be. I'm not sure. There are some indications, but it's very difficult because of the very brief stage it is supposed to be. It is thought to be.
And do you have any candidate you are following up just in case you are able to catch it?
No, not me. I know about some a couple of these water fountains or so, but I'm not studying them.
No, but the other way around, like you've in the last slides you explained the systems for which you have found periods, and maybe you found evidence of systems about to inspire.
Well, the problem is that getting one of them before the common envelope is also difficult, because you have the AGB star, or well, the star evolving through the AGB or at the beginning of the AGB, and the system is surrounded by so much material from the AGB star, from dust and molecules and stuff, that it's very difficult to get to find binaries in these objects, in evolved stars. Very difficult because also the AGB star is much more brighter than the companion. Companion usually is a main sequence star, K or M or so it's very dim, and the AGB is much more bright, and so it's quite difficult to get them. Sorry, I think it wasn't. It's very difficult to get one right starting this process, but
okay,
we have to look into it.
So my last question, I could be asking you a lot, is you said that you found this very fast, I don't recall now if you said fast or massive outflows of molecular material that the central star could not be driving. Do you have any idea of what the driver could be?
Well, the only possibility that there are some possibilities, and in the since I entered the field back in 2002, the debate was over magnetic fields. Everything that we didn't understand, we attributed it, so magnetic fields, that's it. So magnetic fields get the atoms accelerated, and that's it. But if they evolve to this common envelope stage, the ejection could be done at the velocities you need. But alas, there's a caveat here, because models, I haven't told you about this because I prefer to keep things positive, but models of ejection of the common envelope don't really work, in the sense that they need additional energy and additional energy input on top of this orbital shrinkage to explain the velocities we observe. So where does that energy come from? I have no idea. There are more questions. We have been measuring, or estimating rather, the masses, the actual mass of the nebulae, and of this nebula ejected. We know that have been ejected that have undergone this common envelope. And we are finding that the mass of these nebulae is not the same, is much less than the mass of the envelope of the AGB at the time that we suppose the AGB had at the time it entered into this common envelope. So where's the rest of the mass? I have no idea. And
a triple system.
yeah, that's the, you know, now if 20 years ago we thought that magnetic fields explain everything, now we are starting to think that triple stars explain everything. But it's, you know, it's kind of upsetting, let's say, that we resort to triple stars whenever we don't, or any other thing, any other stuff. So there's a lot of questions to answer here still.
Okay, thank you.
Thank you very much. Is there any other question? Okay, there are no questions in the Zoom chat either, so I'm just going to ask a quick one, and then it's well past an hour, so we'll end the talk. So I was wondering whether the like 0.8 to 8 solar masses range, is it flexible? Do all like stars within the range end as planetary nebulas? And are there cases of planetary nebulas outside of the range?
Well, it's flexible in the sense that we still don't know the number very, very accurately. We think right now that it's from 0.8 to 8. Those ranges usually move a little bit, let's say from 0.8 to 1 or so, or 1 point something. And the 8 moves from 8 to 10, let's say. But it's more or less in this range. The sun, I've said 0.8 because that's more or less the last determination or the last estimate. It was about 0.8. And we have been debating whether the sun will actually form one or not. But in principle, all of them between these ranges that we don't really accurately know will produce a planetary nebula. We think. But you see how things have changed in 100 years. So we would be quite wrong in thinking that we know most of this stuff, because there are things that we can be still completely off.
Okay, thank you very much. I'll leave a couple of seconds in case anyone in Zoom wants to raise their voice, and then I'll assume that the talk has ended. So.
Hi, this is Itaskun. Can I ask a question? Hello?
I think Itaskun wants to talk.
Yeah. Hi,
okay.
Hi, Miguel. Nice to see you, at least on Zoom. Thank you very much for the very nice talk. I just have a curiosity. So you touched a little bit the topic about the enrichment, the chemical enrichment produced by these evolved stars. And then I was wondering regarding so the formation of dust, no, because these evolved stars are actually, or they are believed, or they were believed to be the most efficient producers of dust. But you know, some time ago, it was also proposed that supernovae explosions could also be an efficient mechanism for the production of dust. I was wondering, what is the consensus nowadays? So are AGB stars the objects that are producing the largest amount of dust in the universe?
Well, I don't know about the numbers, but we think that the AGB stars produce quite an amount of gas, but I don't know the numbers on the top of my head to compare with massive stars in terms of dust. But we think that they are quite efficient producers of dust, basically with refractory elements condensating first in the top layers of the outskirts of the atmospheres of the star, and then serving as the nucleus of dust particles. But I can't say how much dust in the universe is produced by these objects, or as opposed to massive stars. Sorry.
Okay, thank you. Thank you very much. It was
Thank
really an excellent talk. Thanks so much.
Thank you.
Thank you very much. Anyone else? Okay, doesn't look like so. So we'll end the talk. Thank you very much, Miguel. It was great.
Okay, thank you.